We've got some fresh images of 3I Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system now.
When NASA released the latest data on 3I/Atlas, the room fell silent. The object's energy output, comparable to 10 nuclear power plants, and its precisely timed flybys do not match known natural behavior. What has entered our solar system, and why are NASA officials unusually tight-lipped about their own findings? Join us as we look into the data from NASA's last report on the 3I/Atlas. On July 1st, 2025, the Atlas telescope in Chile picked up something extraordinary, a fast-moving object now called 3I/Atlas. It was racing through space at around 130,000 miles per hour. Within hours, the Zwicky Transient Facility confirmed what astronomers both feared and hoped. Humanity had just welcomed its third known interstellar visitor. But this one wasn't like the others. When Oumuamua passed through in 2017, and later too, I/Borisov in 2019, they behaved in ways that still made sense, at least to some degree. 3I/Atlas was different from the very start. Its path, its behavior, even its light, all of it broke the rules. The Hubble Space Telescope quickly shifted focus, launching a series of detailed observations. What the team found left even seasoned scientists stunned. Normally, as a comet drifts away from the sun, it dims. It loses heat, stops venting gas, and its glow fades. But not this one. 3I/Atlas kept shining with a steady, unwavering brightness. At first, NASA's photometry team thought their instruments must be malfunctioning. They checked, rechecked, and calibrated every system. The numbers refused to change. This object was putting out energy equal to nearly 10 gigawatts, the combined output of several nuclear power plants, all while looking like nothing more than a stray fragment of space rock. For comparison, a normal comet shines because sunlight hits it, melts surface ice, and creates a glowing coma of gas and dust. The brightness varies depending on its spin, its distance from the sun, and how much material it sheds. 3I/Atlas ignored all of this. Its glow was steady, precise, and unnervingly constant, like it had its own built-in power source. Scientists across observatories compared results, desperate to find a mistake. Each new set of data came back with the same story. 3I/Atlas wasn't behaving like anything nature had ever produced. The light curve didn't wobble or flicker the way tumbling rocks or icy bodies do. Instead, it held steady, almost as if the object was deliberately maintaining control, something usually seen in artificial satellites, not natural wanderers from the stars. Dr. Elena Rodriguez, who led the photometric study, said the readings were utterly unprecedented in 4 decades of comet observation. She and her team couldn't match the signature with anything in the astronomical record. If anything, it looked closer to an engineered system than a natural body. NASA released statements confirming the strange results, but carefully avoided concluding. Still, the silence around possible explanations only fueled more speculation. The consistency of the light, the sheer energy output, and the precision behind it all led to an uncomfortable question. What kind of object can hold such perfect control while hurtling through interstellar space? At NASA's Jet Propulsion Laboratory, the top orbital specialists were called together to map out the exact path of 3I/Atlas. What they found kept them glued to their screens day and night. They ran model after model, searching for a mistake in the math. But the numbers held firm. This object wasn't just drifting through space. It was moving as if it knew exactly where it was going. Instead of wandering randomly, 3I/Atlas was threading a path that looked designed. Its trajectory skimmed past Venus, slipped perfectly between Earth and Mars, and then curved toward Jupiter with the kind of precision that human engineers spend years calculating for spacecraft. To test the odds, JPL ran a massive Monte Carlo analysis. Over 1 million possible simulations of interstellar objects. The result was sobering. Less than 0.5/10,000% of random paths could ever produce the same series of planetary encounters. In other words, the chances of this being a coincidence were almost non-existent. Dr. Marcus Chen, the lead trajectory specialist, summed it up in blunt terms. The navigation looked like surgical precision, nothing like what you'd expect from a piece of rock drifting in from deep space. Even stranger, 3I/Atlas wasn't following the usual direction of the planets. It was coming in on a retrograde path against the natural rotation of the solar system, and still managing to time every flyby perfectly. Each planetary encounter gave it exactly the speed and angle change it needed to continue on course. That's the same method NASA uses with probes when they borrow a planet's gravity to slingshot deeper into space. The math behind it was flawless. Seeing those maneuvers in the flight path of an interstellar object was something no one had ever expected. The more analysts dug in, the stranger it looked. The path gave ideal vantage points for observing Earth, Mars, and the gas giants beyond. It was the same kind of route you'd design if you wanted a wide survey of the solar system. There was no doubt about its origin. The hyperbolic path showed that it came from interstellar space, not from within our own system. But the exact way it used gravity assist to hop between planets suggested calculation, not chance. Statistical runs from multiple research groups all came back with the same verdict. The precision was far too sharp to be random. Even its approach angle stood out. 3I/Atlas wasn't skimming along the flat plane of the solar system like most objects. It came in from above, almost like it wanted a bird's-eye view of the planetary orbits. For an outside observer, this would be the perfect angle to watch the entire system at once. Dr. Sarah Kim, an expert in mission design, pointed out that the path looked like textbook gravity assist planning. She said it was the kind of route human mission designers would celebrate if they managed to pull it off, except this one hadn't been built by us. The timing of everything was just as troubling. For 3I/Atlas to hit its mark so precisely, it would have needed to know where every planet would be years, maybe centuries, in advance. That kind of foresight suggested more than blind luck. It suggested planning. The strange flight path was only the beginning. Its readings were so unusual that some researchers began to wonder if the object was hiding its true nature. What kind of chemical fingerprint could look so out of place that it hinted at deliberate concealment? When 3I/Atlas slipped behind the sun in December 2025, telescopes lost sight of it for 2 weeks. But even though the skies went dark and no one knew what was happening, the labs stayed busy. Teams were still combing through the data they had gathered earlier, and what they found was more unsettling than anything seen before. At the European Southern Observatory, Dr. Priya Nakamura's group had been analyzing weeks of spectroscopic readings. The goal was simple: identify the chemical fingerprints that would tell them what 3I/Atlas was made of. The results, however, didn't fit any comet on record. Instead of water vapor dominating the spectrum, as it does with every natural comet ever studied, the water lines were faint, barely there at all. In their place, carbon dioxide emissions overwhelmed every reading. The carbon dioxide lines were so strong, they buried everything else, like a spotlight drowning out a candle flame. This flipped the usual script. Natural comets are dirty snowballs, mostly water ice mixed with dust and rock. As they heat up near the sun, the water vapor produces the signature that astronomers have relied on for decades. 3I/Atlas was the exact opposite. All carbon dioxide, almost no water. Nakamura's team assumed it had to be a mistake. They checked and rechecked their instruments, but nothing changed. Independent observatories in Hawaii, Chile, and Australia ran their own analyses. The results came back the same every time. Even more troubling, the spectrum was missing other expected markers: silicates, organics, trace metals, either absent or showing up in all the wrong proportions. The chemical fingerprint looked stripped down, sterile, like it had been scrubbed clean. The carbon dioxide readings raised other red flags. In normal comets, strong carbon dioxide activity shows up only late in their lives, once the water ice is burned off near the sun. But 3I/Atlas had been releasing intense carbon dioxide the entire time, no matter how far it was from solar heat. The emissions didn't surge or fade. They didn't pulse with rotation the way natural outgassing usually does. The signal held steady, as if controlled. Privately, a few researchers began to ask difficult questions. Could the steady carbon dioxide be exhaust rather than sublimation? Could it be camouflage, a way to hide its true makeup under a chemical disguise? Whatever the answer, the controlled nature of the emissions suggested systems at work, not blind physics. When the first high-resolution images of 3I/Atlas came in, The early numbers pointed to something enormous, maybe 20 kilometers wide. A body that size could, at least in theory, explain the strange energy output simply by sheer scale. But as the data improved and imaging teams filtered out atmospheric distortion, the estimates dropped sharply. Careful photometric work showed that 3I/Atlas wasn't a giant at all. It was small, shockingly small, somewhere between 300 and 1,000 meters across. Dr. Lisa Park, who led the imaging review, said the new measurements completely overturned our understanding of this object. The discovery made the mystery worse. A body no larger than a few football fields was somehow producing the energy equivalent of multiple nuclear plants. That kind of power packed into such a compact frame doesn't happen naturally. No asteroid or comet ever studied comes close. The efficiency suggested by those numbers was far beyond anything in nature. Its small size also explained how it slipped past detection, on its way toward the inner solar system. A kilometer-wide body can hide easily from current asteroid surveys, especially if it doesn't scatter light the way natural rock or ice normally does. The refined profile raised more questions. Natural interstellar objects tend to tumble chaotically, creating uneven light curves. 3I/Atlas showed none of that. Its brightness stayed steady, as if it were holding orientation deliberately. The shape and motion looked more like design than debris. Density estimates added to the puzzle. The mass calculations pointed to something unusually concentrated inside, not the loose rubble piles that make up most comets. High-resolution imaging revealed a surface with almost no craters or roughness, surprisingly smooth for an object that should have been battered by billions of years in deep space. Even the dimensions seemed purposeful. A streamlined, compact form is exactly what you'd want for fast, efficient travel through interstellar space. Smaller cross-section, less damage from radiation and dust, and a structure built to last. Thermal scans deepen the mystery. Instead of heating and cooling with sunlight, the surface held a uniform temperature all the way around, suggesting an internal power source keeping it stable. And the brightness didn't match its size. By every rule of astrophysics, it was far too luminous for such a small body. Dr. Robert Chen, an expert on small body dynamics, remarked that the combination of compact scale and steady energy output was the textbook signs of an artificial probe. Bit by bit, the evidence lined up. Smooth surface, dense interior, stable orientation, controlled heat. A size-to-brightness ratio that broke natural models. Everything about 3I/Atlas looked less like an accidental wanderer and more like something designed, possibly for reconnaissance, surveillance, or data collection during its carefully plotted path through our solar system. The pieces of the puzzle were stacking up in a way no one could ignore, even if official statements tried to sound cautious. If the instruments and analyses all point to manufactured technology, what exactly are the public explanations leaving out? What is being held back when the raw data seems to say one thing and the official line says another? Dr. Avi Loeb, the Harvard astrophysicist who argued that Oumuamua might be artificial, stepped forward with his bluntest take, yet on 3I/Atlas. He said flat out, "Nature typically does not produce perfect trajectories or unusual acceleration patterns without a known driver. Look at the whole stack of evidence, and a pattern appears. The path through our system was hyperbolic. The flybys looked planned. The chemistry was backwards. The size and shape looked like a probe. The energy output behaved like a powered system. Taken together, these are not isolated oddities. They point to the same conclusion from different angles. Official reports named the anomalies one by one, using words like unusual or unprecedented, but stopped short of tying them together. That caution made sense on paper, but it also left a glaring gap between the raw data and the tone of the press releases. The numbers were brutal for any natural origin story. JPL's Monte Carlo runs showed the odds of that exact flight path happening by chance were effectively zero. The chemical makeup did not match comet formation. The power output broke every rule for an object of that size and composition. Independent teams around the world reached similar results. Dr. Elena Rodriguez at the European Southern Observatory said the spectrum was incompatible with natural interstellar objects. Dr. Marcus Chen at JPL called the orbital mechanics indistinguishable from artificial navigation. Experts from different fields were seeing the same thing. Orbital specialists saw spacecraft-style navigation. Spectroscopists saw chemical signs that did not fit natural models. Photometry teams found steady, controlled energy. Imaging showed a compact, smooth structure. Each discipline read its own data, and each piece lined up with the idea of design rather than chance. Every anomaly matched the engineering solutions people use for spacecraft. The gravity assists were textbook. The steady orientation and brightness looked like a controlled attitude. The carbon dioxide-heavy emissions behaved more like chemical exhaust than passive sublimation. The compact, dense build fit a craft meant for long, fast trips between stars. Then there was the timing. Just when the most detailed observations could have been made, the object slid behind the sun for a 2-week blackout. For some scientists, that felt like more than bad luck. It looked like a gap timed to avoid scrutiny. Dr. Sarah Kim, who studies mission design, said it had executed a textbook reconnaissance run. The route gave great observation angles for Earth and the inner planets, and used gravity assists to keep going. If you wanted a fast, efficient probe to survey a system and leave, that path makes sense. Put it all together, and the simplest, most coherent explanation is that 3I/Atlas was a reconnaissance probe sent by an advanced civilization. It had internal power, controlled navigation, possible chemical propulsion for course tweaks, and a compact form built to survive interstellar travel. It did not behave like debris, it behaved like an intent. If that is right, the implications are enormous. We are no longer asking whether life exists elsewhere. We are asking what happens when whoever sent the probe reads their data about Earth. The teams that looked at the numbers did not see natural processes. They saw technology. The question ahead is how the world responds to that fact. If NASA has this much evidence but won't call it alien technology, what else are they hiding from us? If 3I/Atlas was just the scout, what happens when the main fleet shows up with a full report on Earth's defenses? Leave your thoughts in the comments section. Also like, share, and subscribe for more exciting videos. Click on the video on your screen and you will love it.